We started yesterday. We had this, let's see, let me see if I've got the problems themselves. In case there's a question about the problem, I just want to make sure I've got a setup here. Okay. Now I know we did this problem yesterday, but again, I want to get it on the video, and especially for the student that's up front, so when she does the review, she can have it all on one tape. So real quickly, I know yesterday some of you, when we did the answers here, you recognized that you made some errors on your own homework and what those errors were. Remember that when we look at each of these chemical symbols for each of these elements, the number that's in superscript in front of it indicates the atomic mass. Okay? In order for it to be, for example, neon, it has to have, now neon's atomic number is 10. So in order for it to be neon, it has to have 10 electrons, 10 protons. Or let me rephrase it. It has to have 10 protons. To be a neutral atom, it will have 10 electrons. If it has more or less electrons, that's fine. It becomes an ion. If it has more or less neutrons, that's fine. They're isotopes of each other. But if it has different protons, it's a different element. So in order for it to be neon, it has to have 11 protons. And for the neutral atom, it will have 11. Did I say that right? Yeah. Neon's 10, excuse me. That's right. So neon being 10, atomic number 10, means it does have 10 protons. And for the neutral atom, it will have 10 electrons. So the number here has to be the mass. So for each one of these cases, the atomic number, for example, is 40. So 40 protons, 40 electrons. And the difference, 90 minus 40, is 50 neutrons. And that's the process used for every one of them. Neon 22, 10 protons. For the neutral atom, 10 electrons. The difference, 22 minus 10, is 12 neutrons. I may have just said neutrons again. I'm going to slow down a little bit. Because it's neon, it has 10 protons. If it doesn't have 10 protons, it's not neon. In order for it to be a neutral atom, it'll have the same number of electrons as protons. Remember, protons are positively charged. Electrons are negatively charged. So it's neutral when they're the same number. If I have one more electron, it's now negative, negatively charged net. If I've got one less electron, it's now positively charged net. Neutrally charged, same number, protons and electrons. The number of neutrons is the mass minus the number of protons. Nickel, atomic number 28. So nickel 58 has to have 30 neutrons. And radon 222, for it to be radon, it has to have 86 protons. To be a neutral atom, not an ion, 86 electrons. And 222 minus 86 is 136 neutrons. So, any questions on given, first of all, this way of depicting the atom, that you recognize that as atomic mass, and then what atomic mass indicates? Any questions on this type of problem? Okay. Which of the following atoms are isotopes? Now, yesterday there was some question about this. I don't like this question. This question is kind of misleading. So, some of you had some questions about this. You may not have given the book answer. Let me hear how you came up with the answer you came up with, because there's a possibility I'll modify some grades. Now, how should we do this? Somebody that gave an answer that you're pretty confident is the right answer, go ahead and tell me, how did you come up with that answer? Okay, since we're all so confident, let me give you the book answer, okay? The book answer is, which of the following are isotopes? The book answer is those three. Those three are isotopes. Why? They're all sodium, correct? Since they're all sodium, and they all have an atomic number of 11, they all have 11 protons. The varying mass indicates a differing number of neutrons. So they're all sodiums with differing numbers of neutrons. Does somebody else give another answer that they think they can justify? Go ahead.
I had no idea, but I was asking somebody else what they thought about it, and they all said the mass number was like the same. So I put salt, and then I put neon, and then I put magnesium.
That's not one of the answers I would accept. No. Remember, isotopes are the same element. But what did I also say about isotopes? Is there a base isotope? Is there a base amount? No. technically speaking, is neon 22 an isotope? It's one of the isotopes of neon. If there was a neon 21 and a neon 23, yeah, they'd all be isotopes of each other. And magnesium 22, is it an isotope? Well, yeah, it's an isotope. The question should be, which of the following atoms are isotopes of each other? Are isotopes of each other. And for isotopes of each other, then sodiums are all isotopes of each other. But there is no isotope of sodium and a base sodium. That's why neon 22 and magnesium 22 could be, theoretically, isotopes. Yes?
So we just need to look for like the same element.
Same element, different masses. They're isotopes of each other. And that's, I think, what's implied in the question, which are isotopes of each other. Now, if you come back and said, but they're all isotopes because every atom is an isotope of another element, or excuse me, every atom of an element is an isotope of another atom of the element with a different mass, I would go, okay. With that reasoning, this is potentially an isotope of neon. This is potentially an isotope of magnesium. But the three sodiums with differing masses are isotopes of each other. All right, number 3. What is the symbol of the atom made up of 6 protons, 8 neutrons, and 6 electrons? Where are we going to? Somebody else. Thank you. Where are we going to? Ma'am. Pardon? Carbon. Why carbon? What other elements have 6 protons? None. It's the only one. It's like the fingerprint, right? 6 protons. Atomic number 6. 6 is carbon. If it's carbon, it has 6. If it has 6, it's carbon. If it has anything else, it's not carbon. Okay? So it is going to be carbon. Now, what's the question? Go on from there. Go ahead.
The amount of neutrons.
Right. The number of neutrons is going to give us a particular isotope of carbon, right? So all carbons have 6 protons, but we mentioned at least 3 different kinds of carbon. They're all isotopes of each other. So carbon always has 6 protons, but it can have a different number of neutrons. So you identify it how? With its atomic mass. It's carbon-14. This atom is a carbon-14 atom. How do I know it's carbon-14? It's carbon, so it has 6 protons, or it has 6 protons, so it's carbon. Why is it carbon-14 as opposed to carbon-12 or carbon-13? It's carbon-14 because 6 protons plus 8 neutrons equals 14 for its atomic mass. So it's a carbon-14 atom. It's not enough to say it's a carbon atom. It's a carbon-14 atom. Okay? If it had 6 protons and 7 neutrons, it would be carbon-13. Or 6 and 6 would be carbon-12. The vast majority of carbon is carbon-12. Carbon-14 is, well, you know carbon-14. Where do you hear carbon-14 at all the time? Have you heard about carbon-14? Okay. Usually with regard to carbon dating. Carbon-14 decays to carbon-12, decays. And so there's a paradigm that you can use to figure out the age of something. But there are several assumptions in it which I have trouble with, but that's beyond the scope of this class, okay? But carbon-14 is a very small percentage naturally occurring. It starts high, but it decays. And so by determining the percentage of carbon-14 in something, you can figure out how long it's been decaying. That's the principle. Okay. Number 4. If light has a frequency of 2.4 times 10 to the 14 hertz, what is its wavelength? Okay, so how are we going to solve this one? We've been given frequency. We've been asked for wavelength. We need some way to translate. Go ahead.
You want me to switch it up like it's supposed to be, or just give you the formula?
Yeah, either way.
Wavelength equals constant over frequency.
Okay, which constant is that? We use a c, speed of light. The hook here between frequency and wavelength is the speed of light. The speed of light is the physical constant. Wavelength times frequency equals a constant speed of light. And we can rearrange that to solve for wavelength as equal to the speed of light divided by the frequency. or frequency is the speed of light divided by the wavelength. So if you remember it as this way or the other way, you can also remember it as c equals lambda f. And then whichever one you're looking for, divide both sides by the other. Okay? So however you remember it, whichever format, lambda equals c over f equals c over lambda, or lambda f equals c. They're all saying the same thing, just arranged a little differently. So we have a formula that's going to help us translate from frequency to wavelength by plugging in speed of light constant divided by the frequency given.
I forgot if you told us or not, but when we take the test, we have those formulas all there and we have to memorize.
The formulas, the two formulas, you have to memorize.
We don't have to memorize the concept.
Don't have to remember the constants. Right. So wavelength is equal to 3.0 times 10 to the 8th meters per second divided by 2.4 times 10 to the 14th hertz, which is equal to a 1 per second. Now, again, I encourage you to approximate the answer before you punch it in the calculator just to make sure you're right. If you see here, look at the coefficients. You've got a 3.0 divided by a 2.4. It's a little bit less than, what, 1.5, right? It's going to be a little less than 1.5. 3 divided by 2.4. And then what's the exponent going to be? Times 10 to the what? Right now, in your own mind, it's going to be 3 divided by 2.4 times 10 to the something. In your mind, what is the something going to be? It's going to be times 10 to the, again, in your own mind. Do you have it? Okay. What is it? -6, right. It's times 10 to the 8 minus 14. Because remember, when you're dividing by scientific notation, the exponents, when you divide by scientific notation, you do that functionally or process-wise by subtracting them. Subtract the exponent of the numerator, which is 8, minus the exponent of the denominator, which is 14. 8 minus 14 is -6. Okay. So 3 divided by 2.4 is 1.3. 10 to the 8th divided by 10 to the 14th is times 10 to the -6th meters. Questions of converting from frequency to wavelength? That's what this is. And you should equally be able to go from wavelength to frequency, right? Using a rearrangement of the same formula. Opportunity for questions. Okay, and I also look around the room not only so I can hear you going, like if you're trying to ask a question, but you just can't do it. That's why I look around the room too. Because if I look at you and you don't have a question, but you're going, then I assume there's a question there. But I don't see that face right now. I see some tired people, but not, okay, here we go. What's the energy of a light wave with a frequency of 9.8 times 10 to the 20th hertz? Okay, and our first step in doing this process, we're going to energy, right? How do we figure out the energy? Go ahead.
Use the formula E equals Planck's constant times 10.
Right. Energy is Planck's constant times the frequency. We're going to be given the constant. We've just been given the frequency, so we have everything we need to solve for the energy. Energy equals H times F. And I know some of you, even though you wrote it out, then you put a divide sign in there. You know, and you get -50, something to the -54th or 53rd. Okay, if you write down H times F, make sure you do the right mathematical process when you actually work it out. So 6.63 times 9.8. Do you see that that's a little bit less than 10? But for our estimation, let's go ahead and say it's times 10. So 6.63 times 10 would be 66.3. 66.3 times 10 to the -34th plus 20 is -14th, right? Okay? 66.3, the math comes out to be 65 times 10 to the -14th, or 6.5 times 10 to the -13th. So you can see the estimations are close. So you'd be confident in that. Question about that?
Why do you change the exponent again?
Because the form, in my estimation, it would have been 66.3 times 10 to the -14th. 66.3 is improper form. Right, so I have to move it over so there's only one place before the decimal. Since I made it look smaller, I need to make this larger, and I make it larger by going from -14 to -13. All right? So again, looking at your paper, hopefully you see what you did wrong. Or if I made a mistake, you need to speak up. Don't just say, Mr. Baker's always right. I know, theoretically, but not actually, okay? So if I make a mistake, I need to hear it too. And I don't assume the book is always right either, because the book has mistakes in it. Those of you that have first printing, you have more than a couple in there. And I'll make sure that you know the ones that are significant when we get to them. But any questions on number 5? We're almost halfway done. And the end's easier. Electron configs, man, it's a breeze, right? But we got to get through this one first. Number 6, if a light wave has a wavelength of 712 nanometers, what's its energy? Okay, so right now, how do we determine energy according to this module? Energy is equal to what? We just did it. Planck's times F, frequency. Do we have frequency? No. We have wavelength. Can we get the frequency from wavelength? Right, using C equals lambda F. So we have a 2-step process here, right? We need to go from wavelength to frequency to energy. Now to go from wavelength to frequency, first of all, what I'm going to do is take my 712 nanometers, and I'm going to write it in scientific notation for meters. Do you see that though this is an improper form, 712 times 10 to the 9th, it's not the proper form. But if you replace nano with times 10 to the negative 9th, it's another way of representing it, but we've just messed up our sig fig things. So we're going to go ahead and change this. Actually, we haven't messed up sig figs. What we've messed up is proper notation. 712, it becomes 7.12. When we change its form to 7.12, we've made this appear smaller by 2 places. We need to make this appear larger by 2 places, which takes it from negative 9 to negative 7. Okay? So 7.12 times 10 to the negative 7 meters is the same as 712 nanometers. Now that I have it in that form, I can compute the frequency using the formula. Frequency is speed of light constant divided by the wavelength. So plug that in. Now we've got 3 divided by 7. It's a chunk less than half. So let's just say 0.4 for estimation. 0.4. And the exponent is going to be 8 minus a negative 7. So what's 8 minus a negative 7? 8 minus a negative 7 is the same as 8 plus 7, right? Subtracting a negative is the same as adding a positive. So 8 minus a negative 7 is the same as 8 plus 7. Who in here can do 8 plus 7? Oh, where are all the hands? Okay, good. Whew. 8 plus 7, 15, right? I'll go down to the 1st grade and see how they're doing on that, and then we'll come back to the 11th grade. Sorry, I almost called you 10th graders. Come back to the 11th grade, 10 years later, and you're just a little bit slower than the 1st graders. Here we go. So 0.4 times 10 to the 15th. Okay, so 0.4 to the 15th is 4 point something to the 14th. So I know I'm in the right ballpark. So when I punch it out in the calculator, 4.2 times 10 to the 14th hertz. Was I asked for the frequency? No, keep going. Always check your answer and see if your answer answers the question asked. Because some people just said, okay, the frequency is this. I'm like, great. You weren't asked for that. You were asked for energy. You're halfway done. Keep on pressing. So now that I have frequency, I plug it back into the energy equation, which is Planck's constant times frequency. Planck's constant's given, times, and I had to do this just because it kind of sits on the, it's a little hard to see over there. So this should be right up next to it. 6.63 times 10 to the negative 34th joules per hertz times the frequency you just calculated, because that is the frequency when that is the wavelength. So the energy is the Planck's constant times the frequency. I've got 6.5 times 4. Ooh, a little harder math. 6.5 times 2 would be about 13 times 2 is 26, right? So 26 times 10 to the negative 20th, which 2.8 times 10 to the negative 19th. I can live with that. My estimation's close, so my calculator says 2.8 times 10 to the negative 19th joules. Was I asked for joules? Was I asked for energy? Yes. I'm done. Okay. Press till you answer the question that was asked. To know to go from wavelength to frequency and from frequency to energy is the first thing you've got to understand. And then just keep making sure you move through the entire process to get the answer, to solve for what you were asked for. Right? So two-step process, and we've done both those steps before. So any questions on number 7? We good? Okay. Or that was number 6, excuse me. Number 7. Now we get to the fun, easy stuff. One electron is in the 2s orbital, and another is in the 3p orbital. Which has the higher energy? Okay. This is really, really difficult, okay? Because do you remember what the number in front of the orbital indicates?
How high is energy?
The energy level. So again, let's go back to first grade math. Which is bigger, 3 or 2? 3, right. So the higher energy is the 3p orbital, because 3 is bigger than 2. Now, what's the shape of each electron's orbital? We've got a 2s orbital and a 3p orbital. What shape is the s orbital in? S, if you think of it as sphere, it's the ball, right? An s orbital is a spherical, simple ball. What's at the very center of that ball? Or the nucleus. Just say the nucleus. The very center is the nucleus. The very center of every orbital in the atom is the nucleus. They all have a common center. They're all centered on the nucleus. So the 2s, we're going to say, is a sphere. What about the 3p orbital? P's are always dumbbell shape, right? Figure 8, however you think of it, 2 balloons tied together. But remember, the p's, there are 3 of them for each energy level. And so there's a total of 6 electrons, because there's 3 orbitals with 2 electrons each. Yes?
Are lobes fine with that too?
Yeah, I understand that as lobes. But so each orbital has 2 lobes, right? So that's why. The S is spherical and the P is dumbbells. Or balloon animals, or however you want to. No, say dumbbells or lobes. But I prefer dumbbells because it shows that dumbbells are figure 8s, because it shows you understand that like an infinity symbol, but in 3 dimensions. And where it crosses itself right there, that's the nucleus. That's the common point. Number 8, give the full electron configuration for the following atoms. Okay. See how much easier this is when we do it together? For those of you that labored for hours on the homework. We've done 7 of them in just about, what, 25 minutes? Granted, I'm kind of leading you along. But the pain of sitting there and figuring out, that's learning, okay? Now you're going, oh, got it. That's because you went, I don't get it, for a while. You can't get here to the side of knowing until you've labored through the pain of not knowing. It's just part of it. Okay? So if your decision is that you want to learn whatever's easy, you're done. But remember, when you stop learning, you die. So if you want to keep living, you keep struggling. Which is why I spend about 7 or 6 hours a night reading and writing and working on papers. It's just, that's living. Well, I'm in an odd point in life, so I understand that. But anyway, let's go back to the problem at hand. Give the full electron configuration for the following atoms. So I'm not going to even pretend to know what all the names are. I tend to, but I don't want to mess it up. But we're going to look for V. Anybody find it? 23. V is 23. So we have to place 23 electrons, right? Now, whether you do it by slant diagram or whether you do it by periodic table, I really don't care. But make sure you know a way to do it. I'm going to go ahead and use the periodic table because it's very visual. It's right there in front of the class. Sorry, it's not on camera when I step over there, but hopefully you'll be able to walk it through with me. So we're going to place up to number 23. If we remember that helium is supposed to be, or could be, over here next to hydrogen for the 1s, let's go ahead and walk through the configuration. We're going to have a 1s2, then 2s2, everybody chime in, 2s2, and then we're going to have 2p6, 4s2, 3D, right. So 3D3. See that? So make sure you remember to take, once you hit the D block, the energy level goes down 1. And that's very significant when we start getting into compounds. It's very significant that you lose that energy level. Because right now, if I ask you, where is the highest energy level electrons in this configuration? Your response would be the 4s. Right, the 2 electrons in the 4s. They are the highest energy level. How do I know that? Because 4 is greater than 3. But the 3D filled after the 4s, which means your valence shell is going to be that 4s2. It gets a little wonky, okay? So again, it'll make more sense soon. Okay, N is nitrogen, right? Atomic number is 7, so let's count up those 7. So we've got 1s2, 2s2, 2p, 2p3. 2p or not 2p? That is the question, right? Okay. Over here. So 2p3. 1s2, 2s2, 2p3. Ah.
It's gonna be like the whole slide.
55. Cesium 55. So we're just going to keep, you're just going to keep going till we get to 55. So here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s1. Sounds like a chant. We can all just keep going through it, right? Any questions on how we came up with those full electron configurations? Because again, when we get into the abbreviated electron configurations, if you use the slant method, you have to kind of go through the whole thing. But if you use the periodic table method, it just makes life so much quicker and simpler, right? Because what we're going to do, remember, is find the element, go up one row and all the way to the right and find the preceding noble gas, write that in brackets, and then count up the configuration from there. So we'll do the same little chant we just did, but it's going to be pretty short because it's probably only going to include maybe a couple of S's, maybe a few P's, or maybe a few D's. But you're not going to have this long string of electrons. You're going to have the noble gas, and then you're going to have up to, but not including, the next noble gas. So, Ti. Where are we at over here for Ti? All the way down here at, is this the, oh, no, 22. That's TL. Ti is over here. Okay. And that's why the fonts, that's why I switch over to Times New Roman, because capital I's, like right here, some people get confused with lowercase l's, which you shouldn't because it's, right, it's a chemical symbol. The first is supposed to be a capital, but still causes problems sometimes. So for Ti, 22. Since we're doing the abbreviated, we go up one row and all the way to the right, and what is the noble gas? Argon. The preceding noble gas is argon. Let's count up from argon then. We get 4s2, 3d2. Right. S, sulfur, atomic number 16. Is that right? Yep, 16. Preceding noble gas is, okay, so we're going to count up from neon with 3s2, 3p4. And lastly, rubidium, number 37. Right over here, column 1, 5th row. Preceding noble gas is krypton, and all we have is 5s1.
Are we going to do anything with the F block on the test, or have to worry about that?
No. Number 10. Last question. I'm right. It is the last question, right? Okay. What's wrong with the following electron configurations? Yes, ma'am. What's
For A, there's no such thing as a 3p7.
right? There's no 3p7. It only goes up to 6. And 3d9, not 4d. Because as you're filling, it's the d's are always one energy level lower than the preceding fill, right? So whatever the s is, the following d has to be one energy level lower. So it's been 3p6, then 4s, then 3d. All right, what about the second one?
The 3 orbital can't come before the 4s orbital.
Correct. Matter of fact, both of these are in the wrong order, right? Because the s has to precede the d of one energy level less. So 4s would fill before the 3d. All right. Now we get to the fun part. The unscripted free review. We could play Stump the Chump. Why does everybody look at you? I wasn't talking about him when I said Stump the Chump. Talking about me. No, kidding. Let me go ahead and kill the projector. That way we can use the whiteboard, maybe answer some questions if you have any. Okay, now having reviewed all of the review questions and practice problems, and having looked at the EPPs, are there any in particular that you'd like to go over? Yes, ma'am.
Is there one that was kind of like the one where you had to find the energy and the frequency?
Is there one? I asked you to review it. I didn't review it. Let me go through and look. What is the frequency? What's the wavelength? What's the energy given frequency? What's the energy given wavelength? Number 6. And there's number 6 is find the energy given the wavelength. Number 7 is find the wavelength given the energy. So you could work it either way. For number 6, let's just talk through the strategy then. Number 6, this is EPP 6, module 3. What is the energy? So we're going towards the energy, right? Given the wavelength. But we know our energy equation doesn't use wavelength, it uses frequency. So I've got to go from wavelength to frequency to energy for number 6. So given wavelength, I need to find frequency. Given frequency then, or determining frequency then, I have to determine the energy. For number 7, it says what is the wavelength? So I'm going to wavelength. Given the certain energy. Well, again, with the equation, I can go from energy to frequency, and I can then go from frequency to wavelength. Because remember, when my energy and then those two formulas, they're the only two formulas for the module. So this one will take me from energy to frequency, and then this one will take me from frequency to wavelength. Because if I have here I'm solving, well, depending on which one I'm doing, but just by rearranging that formula. You know, if you want to get real fancy, like on this one, you're going to energy. Well, rearrange this. The frequency is equal to the speed of light divided by wavelength. We stick it back in here. There you go, your combined formula. Okay, but just in principle say I've been given what? For number 6, I've been given a wavelength. I need to go to energy. It's a 2-step process. I don't have a formula that'll do that, but I can go halfway. And I can go the other way, the second step, using the other formula. This is the same way. I'm given energy. I need to get to wavelength. I got to go through frequency to get there. So I have to use both. And frankly, if these are the only 2 formulas, and we're trying not to have 100 questions, you know, you should plan on having a 2-step process because I can test your knowledge of both equations with one problem if I use a two-step process. Number 2, if you have a yellow light bulb and a blue one, which one emits the largest wavelength? Yellow and blue. Wavelength. Roy. Iv, right? So the bigger one is the yellow. If it's at a bigger wavelength, it has a smaller frequency, and because it has a smaller frequency, it has a lesser energy. So, which is the longest wavelength? Yellow. Which is a higher frequency? Blue. Which is more energy? Blue. And which is the fastest? That's the little wrinkle in there, isn't it? Which of those two lights? Yeah, we're done. Thank you. Which of the two lights are the fastest? I've got one vote for yellow. Do I hear blue? Do I hear blue? Do I hear blue? Okay, what is the speed of light? What is the speed of light? Isn't it a constant? Aren't they both light? Aren't they both traveling at the same speed? Because the speed of light is constant. The color, see, because one of them has a greater wavelength, the reason it has a lesser frequency is because the speed is constant. If the speed weren't constant, we could not go from wavelength to frequency, because there would be no constant that's holding it all together. So you can determine which one is longer wavelength, which one is greater frequency, which one has more energy, because they both have the same speed. And the brighter one would have a brighter light of the same frequency, two lights the same color, one is brighter. The brighter one has a larger amplitude. So brightness is amplitude. Color is wavelength or frequency. All right? Pardon? Which one is fastest? Both or neither? Right? Because they're constant, they're the same. There's wavelength, frequency, frequency, wavelength, energy, electron configurations, full and abbreviated, and what's wrong with them. So just you'd say, what is wrong with the configuration? Just make sure you look, either do the slant diagram or look up at the periodic table and walk through what the configuration should be and match what you say it should be with what they write down and find where there's discrepancies. Now again, let's look at it real quickly. I would assume that they're either going to be inappropriate amount or inappropriate order. So, looking at it real quickly, I'm looking for P's that have more than 6, D's that have more than 10, and then the next thing would be D's that are not following a higher level S, kind of as a strategy. And if you can't see it, then just go do the fill and compare what you get with what's on the config.